Hi, welcome back. So we are now on the week 8, and in this week, I'd like to introduce you to the unsupervised learning algorithm. One is the principal component analysis, and the other one is the Gaussian mixture model. Okay, in today's sessions, I will introduce the principal component analysis, and I'd like to discuss how we're going to derive so-called principal components. And then we're going to take a look at one example to see the importance of the principal component analysis. So what is the PCA, principal component analysis? PCA is a method for compressing a lot of data into something that captures the essence of the original data. Right. So probably you cannot get the what this statement means. So we're going to take a look at the examples. All right. So if you see this graph, you can easily see there is some diagonal variations on the data in addition to these two axes. Right. So I can draw a certain line. So we see some variations on the diagonal, right? On the diagonal line. And the data points are spread out along this line. And I can say that the maximum variation in data is in between this point and probably this point. And we can also see that data points are also spread out a little above of this line and below this line. So what I can say is the second largest amount of variation is probably from this point and to this point. So there is some variation of the data along this line. So if we could rotate the whole graph, having this center, like this, probably two lines I draw can make a new coordinate, x coordinate and y coordinates. And that makes this horizontal variations and the vertical variations easier to see. So data varies a lot along this line horizontally, and data also varies a little bit along this line vertically. Right, so we need no more these diagonal variations in addition to these two axes, because with this graph, we already capture the two directions, horizontal direction and vertical directions, that can have the variations. These new axes that describe the variations are called principal components. The first principal component, I will say principal component 1. Principal component 1 capture the direction with the most variation in the data. And you see that? So this principal component 1 capture the variation of the data in is kind of the maximal the variation of the data. And I will say this is the second principal component. So PC2 is the axis that spans the second most variation in this data. And we could see that the PC1 and PC2 are orthogonal to each other. And so that is the basic, the concept of the principal component analysis. Basically, through this analysis, we try to find out those principal components. So the formal definition of the principal component analysis is as follows. A statistical procedure then uses the orthogonal transformations to convert the set of observations of the possibly correlated variables into a set of the values of the linearly uncorrelated variable called principal component. As we see that the principal component we derive are orthogonal to each other. So let's take a look at the example on this slide. So we have the data point on the three-dimensional space. So we have the three different features, okay? And then we plot it. And as you can see that along this line, called the first principal component, along this line, the data varies a lot, right? And then we can also think about another principal component, and along with directions, the data spans also a lot. So if we consider two principal components and express the whole data, so what I mean is you try to think about the hyperplane generated by two principal components, and then all the data are projected on the hyperplane. And then you can easily express the data in this form, and you can easily see that you can identify some natural group of the data, which is hardly seen in this three-dimensional space. So the alternative expression for the formal definition of the principal component analysis is in the PCA, we try to find the orthogonal basis that well represent the data distributions. So well represent means the direction which maximally preserve the variance of the data distributions. So as we see in this slide. Right, so this slide shows the, I'd like to, through this slide, I'd like to explain the concept of the so-called the maximally preserved variance of the data. Probably, what is the meaning of this? I think this animated GIF will well explain and the concept of this terminology, maximally preserved the variance of the data. All right, so if you take a look at this graph, the data is varied along this diagonal line, right? And you can see in this graph, and there is a line which is rotating, right? Rotating, and what you can see here is when the line is rotate, you see the red dot. The red dot represents the projected value of these data, right, onto the line. So as the line rotates, the projected data are condensed and varied. It changes according to the angle of the line. And through the PCA, we try to achieve the maximum variation of the data. So we'd like to have the maximum variance in the data distributions among the projected values. In other words, the red dots on this line. So what we can see here, when the line is matched with this pink line, right? And we see that the data is maximally distributed. So that is something we'd like to find out, because by doing so, we can easily distinguish the data points along this line. So why we talk about the principal component analysis, right? So basically, the principal component analysis is a method for compressing the data into something that captures the essence of the original data. So we try to find out less number of features that explain the original data well. So that is the kind of the purpose of the principal component analysis. So what does that mean? We can take a look at this the example. So we can think about the data point on these three-dimensional spaces, right? So you can see the characteristic of the data well, but it is sometimes it is somehow difficult to see, so what is the main characteristic of the data? And if you think about this one, if you think about the one-dimensional spaces, and if you project all the data into one-dimensional space, it's hard to see the main characteristic of the data. So there is something in between two extreme cases. So let's think about if you project all the data point in the three-dimensional space into two-dimensional space, so that you can easily the data point on this two-dimensional space will capture the essence of the characteristic of the data, right? And normally, when the number of the feature increases, the classifier performance initially increases and then eventually decreases, right? So there is some optimal number of features, and by using the principal component analysis, we can identify the so-called optimal number of features, and with the less number of features, we can explain the characteristic of the original data, right? And there are some other reasons to talk about the principal component analysis. So basically, we try to extract the most important information from the data distributions, and at the same time, we try to compress the size of the data set while keeping only important information. And by identifying the key features, we can simplify the description on the data set. And that makes us easier to perform the analysis. Especially, we try to analyze the structure of the observation and variables in the PCA is used. Right. So in this slide, I'd like to provide you overview of the PCA. In other words, we try to find out the so-called principal components. So basically, PCA can simply regard it as finding orthogonal bases that mostly preserve the variance of the vectors projected onto the space generated by the orthogonal bases, right? So by doing so, we try to formulate the optimization problem as follows. So for each time, we'd like to find out the principal component that preserve the maximum variance of the vectors projected on the space on this the principal component, right? So basically in the optimization problem, the decision variable is to find out the orthogonal basis, the principal component. And the objective is to maximize the variance of the projected vectors of the data vectors onto this unit vector, right? If you think about the animated GIF I presented before, so we try to find out the line that maximizes the variance of the projected data vectors on the space, right? So our focus is to find out the line, right? In other words, the unit vector. And in other words, that is the principal component. And to understand the concept, you should understand some concept of the projection and the variance. After that, we try to solve the problem and by using some Lagrangian relaxations. And we can find out by solving it, we can identify the principal component. And then we keep doing this again and again to find out the first, second, third, and so on, the principal components, right? So before introducing the details about the principal component analysis, I'd like to briefly go over the mathematical background related to the PCA. Right, so one is the projections. let's say we have the three data vectors, x1, x2, and x3. And let's think about our vectors. Right? So you can project all the data point xi onto the line. Right? So let's say xi prime is the projection of the xi onto the vector w. Right? So x1 prime, x2 prime, and x3 prime. And we can easily express the x prime by using the w and x. So x prime, whose column is the projection of the xi's onto the w, x prime is equal to w transpose. The w is a vector, right? W transpose the x, where the x consists of the columns of the data vectors. Okay, so you also need to understand the concept of the eigenvector and eigenvalue. Probably you already learned through the prerequisite course for the Mathematical Fundamental for Data Science course. Anyhow, let's think about the vector A. So you can find out the v and lambda. Lambda is constant and the v is the vectors. And that satisfies this equation. AV is equal to lambda v. If so, the lambda is called the eigenvalue of A, and v is called the eigenvector of A. And you can find out more than one eigenvalue, one eigenvectors, right? And there's some characteristics, some property of the eigenvectors and eigenvalues. And if A is non-singular, and there exists the eigenvalue and eigenvector pairs, and at the same time, eigenvectors are orthogonal to each other. And you also need to understand the concept of the Lagrange multiplier. And basically, we can use the Lagrange relaxations by using the Lagrange multiplier to obtain some kind of local optimal for solving the nonlinear programming model. So let's think about the nonlinear programming model to maximize fx subject to gx is equal to c. And you can turn this constrained nonlinear programming model into the unconstrained nonlinear programming model by utilizing so-called Lagrange multiplier lambda here, right? So this part can be considered as the penalty term. If x does not satisfy this one, we have this value will be become incurred. So it can be considered as some kind of the penalty, right? And given this unconstrained the functions, we try to find out the local optimum by taking the first order derivative, right? All right, so how we're going to drive the principal components? So before applying the principal component analysis, what we need to do, we need to do some kind of pre-processing. So basically, in the pre-processing stage, we need to center the data so that the mean of the data distribution becomes 0. So we have these types of data, and then after centering, the mean of the data distribution becomes 0. So that makes the mathematical expression much easier. Also, that makes the calculation also easier. So after centering the data, we try to find out the first principal component. And to find out the first principal component, let's think about the optimization problem. So let's say W is the unit basis. That is the decision variable we'd like to identify, right? And the X is the matrix whose column indicate the data vector, right? So as we remember, the previous slide, this is the projection of x onto the w, right? And because the data is centered to 0, right? So this is kind of mean of the data. And the variance v after the projection x onto the w is expressed in this way. So if you do some calculations, it is straightforward to arrive this one, right? W transpose x, x transpose w. And I can write this part as ds, which is nothing but the sample covariance matrix when the x is normalized, right? So the variance of v after projection x onto the w is expressed w transpose xw. And we try to maximize this variance, all right? So if you think about the optimization model, we try to identify the principal component 1, which is the solution of this optimization problem. We try to maximize W transpose SV, which is the variance after the projection, right? And subjected to, we'd like to identify the unit factor. So if you solve this optimization problem, right, then must be the principal component, the first principal component. And we can find out the second, third, fourth principal components. Because we have for the n-dimensional space, we would have n number of principal components. So let's think about how we're going to derive the second principal component, right? So before taking a look at the optimization model to find out the second principal component, we need to remove some impact of the first principal component. So what I try to do, we try to subtracting the principal component 1 from the x. So we can find out, we can derive the x2 hat. And this step is, by subtracting x, the x2 prime can be calculated by x minus this one, right? So this one is some kind of the impact of the first principal component. So this step is due to getting the flattened data set has no variance along the W1, first principal component. And the second principal component is supposed to be orthogonal to the W1. So by using this data, x2 hat, we can construct the optimization problem as follows. You try to find out the variance after projection onto the after projection of the W2 hat onto the W, right? So we try to maximize the variance, right? Variance after projection of the x2 hat onto the W, and subjected to, the norm of the W is equal to 1. We'd like to find out the unit basis. So if you solve this optimization problem, we can find out the second principal component. Okay, so we keep doing the same thing for the third principal component, fourth principal component, and that is how we do. We subtract the PC1 through PCK-1 from x, right? So we derive the sk hat. So that means that is a kind of the flattened data having no variance along the W1, which is the first principal component, W2, which is second principal component, up to the WK-1, right? And by using this flattened data, and we try to solve the same optimization problem with the xk hat, and that is we try to find out the unit vector, unit basis, then maximize the variance of the projection of the xk hat onto the unit vectors. And that must be the kth principal component. And instead of the iteratively solving the series of the optimization problem, there is some alternative approach, right? So if you take a look at the optimization model, right? If you think about the optimization model, that is the optimization model to identify the principal component, right? So let's think about the Lagrangian functions, which is the kind of the nonlinear, unconstrained version of this optimization problem. And if you take the partial derivative with respect to w, and this is something we got. And if you take a look at this one, we have SW is equal to lambda w. What does that mean? W is the eigenvector of S, and lambda is the eigenvalue of S. So S is the sample covariance matrix, so S is the symmetric matrix, so eigenvectors are orthogonal. Consequently, the principal components are nothing but the eigenvectors of S, right? And by the substituting S with the lambda, right? Because if the W is the eigenvectors, then SW is equal to lambda W, right? So I plug in, instead of SW, I replace it by lambda W. This is how we do, right? And lambda is constant. We can take it out front, and we have the unit vectors. So this is lambda. So lambda represents the variance, right? We try to maximize the variance. So in summary, so given the sample covariance matrix as center for the center data X, right? The eigenvectors, they are orthogonal to each other. They are indeed the principal components, and corresponding the eigenvalues can represent the variance, all right, along the principal component. All right. So if you think about let's say these are the eigenvectors of the S, right? And then lambda, which is the lambda 1, lambda 2, lambda 3, represent the eigenvalues, right? And indeed, W1, W2, W3 are the principal components. And lambda n represent the variance of the projected vectors onto the corresponding the principal component if data distribution is normalized. So the xn transpose x represent the value after projection x onto the wn. And if you take a look at this one, right, and W2 actually preserve this 70% of the variance of the original data. Right, so we're going to talk about some issues on the principal component analysis. So I'd like to remark that for the n-dimensional data point, we would have n number of principal components. And usually, we illustrate the two-dimensional representation with the two principal components, which preserve the variance maximally, and to just to interpret it easily. So what I'm saying is, when you take a look at the subtextbook, they try to express the principal component on the two-dimensional space, but this is not, in the cases you may misunderstood that we only need to identify the two principal components only, but that is not true. You can find out the n number of principal components for the n-dimensional data point, but normally we try to take the first k number of the principal component, because with that principal component, still we can explain the majority of the data well, right? Okay, so the next question is, then how many principal components do we need to use? That is some kind of question, right? So we are not interested in many principal components explain especially small variances. So let's take a look at this example. Let's say the first principal component explain like in a 60% of the variance of the original data. And second principal component explain around the 20% of the data distribution, and so on. This is kind of the cumulative representation. So probably by using the first two principal components, we can preserve the 80% of the data, the variance of the data distributions. So we often use first a few principal components to explore the data, to explain the data as well. So I'd like to introduce one of the example of the principal component analysis, right? This example is the kind of the case that given that you have the face image, you'd like to find out the image after removing these glasses, right? So by using the principal component analysis, we try to remove some kind of noise on the image. So how we can do it? So in order to do so, we use the bunch of data representing the faces having no glasses, right? And each image is represented by as a vector whose element is the value of each pixel. So let's say for each figure, each image, there is a 45 by 40 pixel image. So we have the 1,800 dimensional vectors. It's a huge vector, huge attribute, huge features. So instead of using the whole 1,800 dimensional vectors, we can identify, we can compress the data, right, by using only first 20 principal components after applying the principal component analysis. So these are the first 20 principal components from the 1,800 principal components. So we call it, this is the eigenfaces. So in a descending order of the eigenvalues, high rank the eigenfaces represent some kind of general characteristic of the image, and the low rank eigenfaces represent the individual characteristic of image, right? And the original image can be presented as a linear combination of the eigenvectors or eigen faces, right? So I would say because we have the 1,800 dimensional space, because we can find out 1,800 principal component or 1,800 eigen faces. And the original image can be expressed as the linear combination of those eigenfaces. Right, so let's take a look at this slide. So, for example, the last row represents the image by using the first two principal components or first two eigenfaces. Those look similar, right? Because as already mentioned that high, ranking, having the high eigenvalue actually has the general characteristic of the image. So everybody looks similar, but if you include further principal component, if you take a look at this one, the second row, that also included not only the general characteristic of the image, but also the individual characteristic as well. So you see that the second row maybe well capture it looks similar to the original image, right? So using many eigenfaces can construct similar image with the original, but with this less number of principal component or less number of eigenfaces, still we can generate the images which is quite similar to the original image. So with the less number of information, we can still represent the whole data, right? Original data. So in the today's sessions, we talk about what the principal component analysis is, and I also explain and how we're going to drive the principal components, right? And also we took a look at one of the interesting example of the principal component analysis. And as we see that, with the less number of information, we can still represent the whole data, quite well. That is the main concept of the, principal component analysis. So, that's it for today. Thank you.